So Dr. Pedersen will be our first panelist, and he hails from right here at the University of Victoria. He's currently a professor of paleoclimatology and marine geochemistry and served as the Dean of Science with UVic for 6 years. In 2009, he was appointed the founding executive director of the Pacific Institute for Climate Solutions, an important organization that serves to connect climate science to solutions for local policy and decision makers. In 2015, he stepped down from that role to pursue research and the authoring of a book on BC's climate action history and experience. Welcome, Tom.
Well, thank you, everyone, and thank you for coming tonight. I'm not going to speak for very long, I hope. As you all know, climate change is an issue that could take days to explain properly, and we're not going to do that tonight. I'm just going to run through some of the background of the changing world around us as induced by global warming, as it pertains particularly to Saanich. And so the one word I'm probably not going to focus much on tonight is opportunities, and I hope we'll have time for discussion about that later on. But I do want to say a few words about climate change impacts. And I want to start with this photograph. This is Saanich, as taken from the far side of Saturn in 2006. And as you can see, it was a little far distance away, 1.2 billion kilometers. Cassini spacecraft was a remarkable NASA achievement that spent many years photographing Saanich, going in orbit around it and through the rings and one thing another. It was told by NASA to crash into Saturn last September, but it sent a remarkable array of photographs back to Earth during its time in orbit. In this photograph is Saanich, or more precisely, Earth. And you might say, where is it? And those with sharp eyes can see exactly where it is. It's right there. That little dot is where we live. It's the only dot in the entire universe that sustains human life as we know it today. The only one. And it does, I think, put into context the importance of sustaining or stewarding the ability for a human species to survive on that particular planet. When we zero in, of course, Saanich is sitting here. Saanich is sitting right there. It was actually a cloud-free day. It's right there. You can just see that little gap in the clouds. But the important thing about this photograph is if you look kind of carefully, you can see it's fuzzy around the edges of the sphere. And that's because we have an atmosphere that's refracting light. And so when we look around here, you can get just a sense that there is an atmosphere present on Earth. And that atmosphere is what sustains us, of course, and we are abusing it. And we've been abusing it for quite a considerable period of time now. And one of the great additions to that atmosphere that we have been contributing as a human species, of course, is carbon dioxide through our consumption of fossil fuels and through deforestation. When I was a young man, actually when I was born, it was over here. That's how old I am. It was just off the edge of this in 1951. And at that time, the concentration of CO2 in the atmosphere was about 310 parts per million by volume. As of this morning, it was 409.26 parts per million by volume. So that's an increase of about a third in one human's lifetime. We've never seen in the entire geological history of planet Earth a rate of change in the carbon dioxide concentration in the atmosphere that matches what you see here on the screen. It's never happened before in the entire history of planet Earth, to the very best of our geological knowledge. And if you look really closely at this, what you can see, of course, is that it's nonlinear. That curve is actually an exponentially increasing concentration of CO2. We've known since 1896 that the Earth was going to be warming by our contribution of carbon dioxide in the atmosphere from burning fossil fuels. And yet we've done nothing about that of any substance. And so we're seeing this inexorable increase, which is on its way up continuously, and will continue on in that direction for some considerable period of time into the future. Well, associated with that increase, of course, because carbon dioxide is a very effective absorber of infrared radiation or heat trying to leave the surface of the Earth. That surface, of course, warmed by the sun, and as heat tries to escape back into space, carbon dioxide intercepts it. That essentially is the root of the greenhouse effect. And the consequence of that, of course, is the Earth is warming. And there's no argument about this anymore. If anyone does argue about it, then they should take their head out of the bucket of sand and look at what's happening around them. There is no argument. The Earth is warming. We have many, many, many sources of information confirming that. And particularly since 1970 or so, we can see that the warming has been inexorably increasing. It's on the order of a little over a degree now, depending on where you take the baseline back here in the earlier part of the 1900s. There is a lot of variability in the warming record, and things like volcanic eruptions cool the planet by as much as 0.2 degrees Celsius, like Pinatubo did in 1991. El Niños and La Niña events add noise to this record. We went through the mother of all El Niños here in 1997-98, but that was surpassed in 2016 by that El Niño you can see at the top of the curve here. And so there's lots of variability over time. Mother Nature does throw variability at us, but overall we are driving the temperature up at a substantial rate, and we're seeing the impact of that increase now around the world. And here's a really nice example of this impact. I love this data set. This is the GRACE satellites, and some of you in the room, many of you in the room may be familiar with this. GRACE is an acronym that stands for Gravity Resolving Climate Experiment. It's a joint venture between the United States through NASA and the German Space Agency. And these satellites are a pair that are, as you can see, 220 kilometers apart. They're about 500 kilometers up in space. They go around the Earth 15 times a day, over the North Pole and the South Pole, 15 times a day. They have accelerometers on board. They measure the gravitational field below them. They communicate with each other using microwaves. They can tell their distance apart from one another here to 1/10 the diameter of a human hair, and they're 220 kilometers apart. Now, the fascinating thing is that when the lead satellite goes over something that has a slightly higher gravitational pull, like a mountain range, or let's say Greenland, Greenland pulls on that satellite and it stretches it from the trailing satellite. By the way, they're called Tom and Jerry, for those of you who are interested. And so Tom gets pulled away from Jerry when it goes over something that has a significant gravitational pull over mass. Then it passes over that, and Jerry gets pulled back a little bit as it comes over that mass. And so they stretch and contract as they go over changing gravitational pull on the Earth's surface. They do that 15 times a day, and we can, as physicists, we can calculate what the gravitational pull is below it, below this pair of satellites. Well, when you do that calculation, you can see what's been happening to the mass. This is changing mass on Greenland. Over the last 16 or 17 years, Greenland is losing mass, and there's an annual variability in here, depending on how much snow is accumulating. But that mass loss, which is increasing through time, that's not rock. There's nobody mining 300 billion tons of rock from Greenland each year. What this is the loss of ice. Greenland is melting, slowly melting. It's not something that's happening dramatically quickly, but it's progressively melting. That melting is accelerating, and of course that's contributing to sea level rise. And sea level rise is a concern here in Saanich. Sea level is now rising at about just over 3 millimeters per year. And note the uncertainty in that, it's plus or minus 0.4. I first started teaching at UBC in 1980. And I used to give a lecture on the history of sea level on planet Earth, going way back in deep time and then coming forward to the present. I was younger then, and sea level was lower then. It was 1.8 millimeters per year in 1980, plus or minus 0.8. We're almost twice that now, and our uncertainty has been cut in half. and it's continuing to accelerate. And a paper that was just published 2 months ago has very carefully teased out what the acceleration rate is, and it's about 1/10 of a millimeter per year. So 3.2 now, 3.3 next year, 3.4 the year after, and so on and so forth. Continues to accelerate. Greenland is contributing to that. Melting of the West Antarctic ice sheet is contributing to that, about 1 millimeter a year from those sources. Another millimeter a year because water warms when it expands. And we're losing, around the world, our alpine glaciers, everywhere. Doesn't matter where you go, alpine glaciers are retreating. We have 15,000 glaciers here in British Columbia, many of them small. They're all in a state of retreat. So it's warming. The impacts of that are pretty obvious when we look out at the landscape. Now, when we project for the future, and this is where it becomes really important in terms of what we might be doing here in Saanich, we don't know exactly how fast sea level is going to rise as the decades march ahead of us. The best case here is 57 centimeters or so by about the year 2100. And that depends, of course, on how fast we mitigate our emission of greenhouse gases to the atmosphere. The worst case, from the modeling that the scientific community does, is closer to 2 meters. Some scientists, some very smart leading scientists who work on sea level, say that number is too low and that this is just an absurdity. This is closer to reality, but it's too low. Well, we don't know what the truth is yet. We'll have to live through it and see what the rate of rise is. But it's already having a bite in some places. This was published a few days ago. This is a newspaper in Florida. The Sun Sentinel editorial board published this. It's a parallel newspaper to the Miami Herald. Miami is routinely flooding now. Almost every king tide, the streets of Miami fill with seawater. They're spending $500 million now to raise roads and to improve seawalls and so on, to try and hold Mother Nature at bay. But they're going to lose. They're going to lose. Because if the 2-meter sea level rise by the year 2100 comes to pass, people will just have to move away from Miami. Miami will essentially become a ghost city. And that's really what's happening now in many parts of the world. It's not Cadborough Bay, I hasten to point out. And the difference is that the rates of rise here are slightly different than they are in Miami, and there's good reasons for that. And I want to walk you quickly through that. Sea level rise is very much a relative issue. It's a relative change issue. And so if I'm standing here on this floor, and water starts to coming in, but there's a hydraulic cylinder under the floor or something that lifts the floor, then the water would go down, wouldn't it? So if the land is coming up, the water could go down. Or if the land is going down, the water could be coming up. And we have to take that into account when we're looking at sea level here in the Saanich region. So if everything is stable, you put a stick on the shoreline and you're not going to see a change through time. And what could be happening in this case is that on the left-hand side is that land could be rising and the ocean could be rising at the same rate, and you'd never see a difference. But if the land is rising faster than sea level, then we're going to see sea level will actually decline. So it will fall against the stick. Or if the land is sinking and sea level is rising, then we're going to get a more rapid increase in sea level rise. This latter one on the right-hand side is what's happening in Venice. Because in Venice, they've been extracting the groundwater from below the city for industrial reasons. The land has been subsiding, sea level is also rising, and so Venice is very seriously threatened by the future. Well, what does this mean for Saanich? Well, we've got some different factors here that Venice, for example, Venice was not glaciated during the last ice age, but we were. And this part of Canada, we had a big ice sheet that sat over British Columbia and another major ice sheet over much of the rest of Canada. That depresses the Earth's crust with time. Underneath, we have a semi-molten mantle material here, which gets pushed out of the way when you put a lot of mass on top. The crust sags. It takes thousands of years for a mass added to the top to actually come to equilibrium with the underlying mantle. And then when you melt that mass, take it away, the opposite happens, and the crust rebounds and comes back up. Well, we're feeling that here. Even today, we're still feeling that here. We lost our ice right here from southern Vancouver Island. The last ice left us about 11,000 years ago, but the land is still, the crust is still rebounding from that loss of mass. We had, where we are tonight, we had about 750 meters of ice above us, 21,000 years ago during the peak of the Ice Age. We lost that, and the land now is slowly rebounding, and that has an impact on relative sea level rise. We know what the rates are of this rebound, and this is the rebound rate across the northern hemisphere. It's very, very high in the Hudson Bay area, but we don't worry about that here tonight. We're more concerned about the Saanich region over here, and you can see, based on this model result, that we're looking at something on the order of 2 millimeters per year or so, perhaps a little less than that, of rebound rate along much of our coastline here in British Columbia. We have another big effect on relative sea level change, and that is that the crust here is not stable. And any of us who've lived through earthquakes here, we know that we are in a seismically active zone. And that's, of course, because the Juan de Fuca plate right here is diving below Vancouver Island. And as it dives below Vancouver Island, it's pushing up the crust in this region. And so the continent is actually buckling a little bit. And so a place like Tofino here, Tofino is actually rising. And it's being pushed up not so much by isostatic rebound, from that is from the loss of ice mass, but it's being pushed up because of the tectonic buckling that Vancouver Island is undergoing. And we have to take that into account when we're looking at the relative change of sea level. So that side of Vancouver Island, particularly the southwest side of Vancouver Island, is buckling upward. We can measure these things now. You know, the technology that's available to us is really extraordinary. And so we have GPS stations, global positioning system stations, that are quite precise now and allow us over time to measure the vertical velocity in terms of millimeters per year. We have a number of stations on Vancouver Island. Here's Saanich sitting down in this corner. Tofino is up here. And you can see in the vertical velocity in the Tofino area is maybe 4 millimeters per year. In Saanich, it's somewhere between perhaps 1 and 2 millimeters per year in total. And so this is a combination now of the isostatic effect from the loss of ice mass and the associated rebound, and the tectonic buckling from that Juan de Fuca plate diving below Vancouver Island. The consequence of that is that sea level rise varies quite markedly from place to place, even here on Vancouver Island. So Tofino, it doesn't have much to worry about at the present time from sea level rise because Tofino's rising. Over the last 100 years or so, the sea level's actually fallen by about 17 centimeters at Tofino. In Vancouver, though, they do need to worry. Sea level is rising. It's gone up about 2 centimeters over the last half century. And in our region here where we are, along our coastline, it's gone up by about 3 centimeters over the last half century. So relative sea level is rising here. Right now, it's around 1 millimeter per year or so. But that's no excuse for us to be complacent. Because remember, it's doubled during the time I've been teaching. It's already doubled. And the projections are that the West Antarctic ice sheet might start to melt rather catastrophically in the relatively near future, later on in this century. So we have no reason whatsoever to be complacent about dealing with the implications of sea level rise. And of course, there's more to the impact of the ocean on the coastline than just sea level rise. There's a very important concept to do with the timing of particular events. And when we get big storms happening at the same time as a high tide with a higher sea level, and if it happens to be a strong El Nino as well, which does change sea level in this part of the world, then we can see significant flooding, as we did in 1982 on the Fraser Delta. And of course, we can never predict when these kind of events might happen, but the probability of them having greater severity increases, of course, as sea level rises. Finally, The second major concern is extreme deluges or extreme rainfall events. And I wanted to say just a few words about this, and I'll end with this particular impact, because what we're seeing around the world now is that extreme rainfall events are increasing both in frequency and intensity. And the reason for that's really simple. This map is a model projection from the Intergovernmental Panel on Climate Change report of 2013, just showing what the long-term impact of changing precipitation is going to be by about the end of the century. It will be drier in some places and wetter in others, but the key thing here is this description at the bottom. When we warm the atmosphere by 1 degree, the water vapor content increases by 7%. It's a well-known physical relationship that's been known for 150 or so years, called the Clausius-Clapeyron relation. And so every time we warm by a degree, we're adding a fair whack of water vapor to the atmosphere. Now, earlier you saw the temperature record that suggested that temperature has gone up by something on the order of a degree already. And in fact, we measure the amount of water vapor in the atmosphere, and since 1970, it's gone up by 4%. Well, what goes up has to come down, and it does come down. And when you get warm, moisture-laden air hitting a cold front, that water condenses, and what we're seeing increasingly now is extreme rainfall events at the interface between those warm air masses with that additional water vapor and the cold air masses that confront them. And so around the world now, we are seeing a significant increase in flooding. And these are events that have been happening now for a long time, and the scientific community has been mapping them. And this paper that was published 7 years ago now in Nature was one of the first to identify statistically that there had been a statistically significant increase in the intensity of extreme rainfall events. More recently, another paper that was published in 2015 showed increased record-breaking precipitation events under the impact of global warming. And this is well understood physically. If you look at the data, and I've taken from that latter paper in 2015, the latitudinal band in which we sit here in Saanich. These are data going back to the year 1900. There's 111 years of data here, 766 grid points. Here's the number of extreme rainfall events. Essentially, it's the number of record-breaking events. And you know, there wasn't an awful lot that you'd point to up to about 1960, 70, somewhere in there. But then you look at the last several decades, and that's the projection, that's the trajectory we're on now. And we're seeing these things happen all the time. Most recently, you may have seen this in the news last week, in Kauai. And this was an all-time record rainfall event for the United States of America. 50 inches in 24 hours. Now, I don't think in inches anymore, so I converted that. That's a lot of rain in 24 hours. It caused immense damage. It undermined houses, for example. This is a really nice home, as you can see, used to be, not anymore. And so we can anticipate that these events are going to be happening, not just in places like Kauai, but we have to prepare for them here, because we will get hit with extreme rainfall events. They may not be on this scale, but they will be significant. So that immediately leads to consideration of how will our stormwater system cope with that? Are our culverts big enough? Some years ago when I was with PICS, I had a phone call from the city engineer in Kamloops. He said, "Can you help me?" I said, "I don't know." He said, "We're going to replace our stormwater drainage system in Kamloops. We're going to start this year, and we're going to put in bigger pipes, but we want to know how big they need to be for rain in 2060. That's what he asked me. It was probably a 50-year projection. I said, "Well, I can't really give you that. All I can say is buy the biggest pipe you can afford and put it in the ground," because that's really all we can do. We don't know how severe these events are going to be, but you can bet that they are going to be much more severe than they were in the past. The interesting thing about how the Los Angeles Times reported this last week, or on April 28th, was the headline. It wasn't this. that caught my eye. It was the last part. Scientists warn it's a sign of the future. This is the mainstream media now saying things are different now. We have to prepare for this. We have to prepare for a different future. And we have to do it here as much as they have to do it in places like Kauai. So I'll finish up there by just pointing out that we know that global warming impacts are upon us. They're absolutely upon us. They're serious. They are long-term. They're insidious. They're incremental. But they can also be episodic, and it's the episodes that we have to plan for in the future. And so our challenge is twofold. We have to mitigate. This word is not should. It's not should. It's must. We must mitigate. But because we've been so neglectful for so long now as a human species, we also have to adapt. And we have to try and blunt the leading edge of the worst impacts that are coming down the pipeline at us. Thank you.